In these notes, we'll talk about resistors in series and in parallel. Multiple resistors in a circuit can be arranged in several ways. If the circuit forms a single loop, resistors are described as being in series. If I were going to make a sketch of that, I would draw a battery and then a wire, and then here I've got 3 resistors in series. They're just in a row. Since the current only has one path it can follow, the same current goes through all the resistors. So whatever current we would measure with an ammeter, if I were to take and put an ammeter into the circuit, that same current is going to travel through all the resistors. Remember that current is equal to charge over time. Charge in coulombs over time in seconds. Okay, if the circuit contains a point where branching of the circuit occurs to supply the resistors, this is known as a parallel circuit. So a parallel circuit, here I've got a portion of one drawn down here. So here we've got one single wire that branches into 3 different wires. If I were going to draw an entire circuit diagram with resistors in parallel, it might look something like this. So in this case, when the current comes around and gets to this point, it's going to split when it goes through the 2 resistors. If I were to take the total current that I would measure here, that would be equal to the sum of the current in each resistor. So current is conserved because charge is conserved. And that's indicated in this formula here, that the sum of the currents in should equal the sum of the currents out. Let's see. The other thing that we need to know about a situation like this is the potential difference is the same. So remember that in a power supply or in a battery, what's happening is we have an energy increase from the negative side of the battery to the positive terminal of the battery. So the charges are coming through the battery, and as the charges come through the battery, they gain energy. Then what happens is when they go through the resistors, they're going to have the same drop in energy per unit charge. So if this battery were a 9-volt battery, then the charges, which are energy carriers, would have a drop of 9 volts across each resistor. So in parallel, the voltage would be the same. It's the same idea as the change in potential energy for a waterfall. Here I've got kind of a weird picture of a waterfall, but think about these different streams. They all have the same difference in potential energy per drop of water. There are different currents here. There's different amounts of water falling, but the potential energy drop for each drop of water is the same. Okay, so in series, the voltages will add together, and in parallel, the currents will add together. And that's going to have consequences for our resistors. In series, the resistors will sum just by adding them together. In parallel, when we add resistances, we have to add the reciprocals together. And what we're doing here is we're thinking about, let's look at the series first because that one's a bit simpler. Let's say I've got 3 resistors here. Let's say that this one's 5 ohms, this one's 10 ohms, and this one's 15 ohms. In order to create an equivalent circuit, I could put in a 30 ohm resistor because 5 plus 10 plus 15 is 30 ohms. So just to keep this simple, let's say that this is 60 volts here. In both of these circuits, we would have a current of 2 amps, because we know that V equals IR, we know Ohm's law holds, and so 60 volts is going to equal 2 amps times 30 ohms. And that works for both of these situations because the sum of the resistors in the top one is also 30. In parallel, things get a little bit, well, they're not quite as intuitive. Let's think about what happens if I have a, I'm just going to kind of start a new situation here. Let's think about what happens if I have an 8-volt battery. Here's my 8-volt battery. And then let's say I've got a 2 ohm resistor and a 4 ohm resistor. Now we know that in parallel, each resistor has 8 volts across it. So this first resistor has an 8 volt potential drop across it, and therefore I can calculate the current through this. Probably should have drawn this a little bit bigger. The current then must be 4 amps, because again, if I use Ohm's law, V equals IR, 4 amps times 2 ohms, that's ohms, must equal my 8 volts. When I plug in another resistor, what happens? I actually end up drawing more current. Here I must have 2 amps. Again, V equals IR. I've got 8 volts. Must equal 2 amps times 4 ohms. And what happens is when I just had the 2 ohm resistor plugged in, or if I only have the 2 ohm resistor plugged in, then to begin with, I would be drawing a total of 4 amps. But when I plug in the second resistor, now this isn't just 4 amps, it is, oops, I have to add 2 amps, and now I pull a total of 6 amps. So if the current went up, what that means is that the effective total resistance of the circuit must have gone down, because Ohm's law still must hold. In fact, if I've got an 8-volt battery and a total current of 6 amps, I can solve for the resistance. It would be 8 divided by 6, which is 4/3, which is 1.33. And that is less than the sum of the 2 resistors added together. So let's do some examples. Let's do some more examples with this, and hopefully it will make a little more sense as we practice. So here it says a 10 ohm, a 15 ohm, and a 20 ohm resistor are connected in series across a potential difference of 90 volts. So my first task is to sketch this. I'm going to number these R1, R2, and R3. Oops. And that's my voltage. Find the current and the voltage across each resistor. Now, one thing that I like to do when I'm solving problems like this is I like to make a grid. It just makes it easier for me to keep track of what I'm doing. So I've got 3 resistors, which I'm going to name 1, 2, and 3. The first one is 10 ohms. The second one is 15 ohms. And the third one was 20. Okay. So my first step is to find the effective or equivalent resistance. And here my resistors are in series. So the equivalent resistance is simply the sum of whatever resistors I have. So in this scenario, it's going to be 10 plus 15 plus 20 And when I add that together, it is 45 ohms. Okay. Next, I know that my total voltage is 90 volts. I'm going to use Ohm's law to find current. So V equals IR, the total voltage is 90 volts, the current is unknown, oops, and the resistance is 45 ohms. So I would divide both sides by 45, and I would get that my current is 2 amps. Now that current is the same through each resistor. Now here's where making a table really comes in handy. I've got the voltage and the current through each resistor. I'm sorry, the resistance and the current through each resistor. And now to find the voltage, I'm just going to use V equals IR. I'm just going to multiply. So I've got 20 volts, 30 volts, and 40 volts when I multiply. 10 times 2, 15 times 2, and 20 times 2. And notice when I add 20 plus 30 plus 40, it does sum back to my total 90 volts. So I know that I've done this correctly. So what happens, what we would model is we would say that a charge, oh, that didn't work. Try it again. I'll draw one over here. What we would say is that a charge goes through the power supply and gains energy. How much energy does it gain? It gains 90 volts or 90 joules per coulomb of charge. So it's a ratio because the more charge there is, the more energy we get. So it's a ratio of joules per coulomb. And then this charge goes through the first resistor and it loses 20 joules per coulomb of its energy. Then it loses 30 joules per coulomb of its energy. Then it loses the remaining 40 joules per coulomb of its energy, goes back to the power supply to be resupplied with energy, and just keeps going around and around, gaining and losing energy. All right, let's try one with parallel. It says a 10 ohm, a 15 ohm, and a 20 ohm resistor are connected in parallel across a potential difference of 90 volts. Find the current and the voltage across each resistor. Okay, so once again, we've got our 90 volts. And I'm going to make my sketch again. And I'm going to label these R1, R2, R3. And I'll make my table, keep my ideas organized. So 10 ohms, 15, and 20. Okay, now this one is in parallel, and what we know about parallel circuits is that the voltage drop is the same across each resistor. In fact, the voltage drop across each one is 90 volts. So I can still, though, use V equals IR. Oops. I can divide to find I. So it would be voltage divided by resistance. So this would be 9 amps, this would be 6 amps, and this would be 4.5 amps. So the total current would be 9 plus 6 plus 4.5 would be 19.5 amps. Now that solves the question. We found the current and the voltage across each resistor. Just for kicks though, let's find the equivalent resistance. So in a parallel circuit, 1 over the equivalent resistance equals 1 over R1 plus 1 over R2. And you can keep going for however many resistors you have. So we'd have 1 over 10 plus 1 over 15 plus 1 over 20. Now you can solve this with a calculator. You could put in your calculator 10 to the negative first plus 15 to the negative first plus 20 to the negative first, and then don't forget at the end you still have to take the reciprocal of that. So this is what you would enter into a graphing calculator to solve it. Or if you love fractions like I do, you could change this into 60ths, because this would be 6 60ths plus 4 60ths plus 3 60ths. So we get 1 over REQ is equal to 13 60ths. So the equivalent resistance would be 60 13ths. That's kind of gross. As a fraction, and if you want to make it into decimal, it's 4.62. And if we take, let's see, if we take 4.62 ohms times 19.5 amps, sure enough, we get 90 volts. So I guess we also could have just taken our 90 volts and divided to get our equivalent resistance, but we would have gotten the same value. We would have gotten about 4.62. All right. Let's try something a little more complicated. And actually, I'm going to make this into a separate video so you can pause and